Hello, my name is Keith Smith, a Principal Engineer at Perceptive Engineering. Today I am given a short demonstration of how model-based design can be used to optimize the production of formulated products. There are some compelling reasons for following this approach, and here are some of those motivating factors. First of all, we can reduce product development time. Secondly, the model-based approach can help us in understanding how formulation affects product properties at pilot scale and also at commercial scale. Thirdly, a great benefit for the dryer network is that we can ease the introduction of new formulations, and we can have greater confidence in operator parameter settings. The model-based approach also allows us to augment the advanced process control strategies in the network for new critical quality attributes or process parameters. To keep this short demonstration focused, we will look just at the spray dryer and show how a rigorous mechanistic model of the dryer can be used by an advanced process control strategy to optimize powder production. So let's take a look at the spray dryer. Here we have a flowsheet model. Into the spray dryer we have the slurry feed, the drying gas, the dryer itself. The dryer exhaust exits the dryer, goes through a cyclone and a baghouse, and then to atmosphere. The powder product comes out of the dryer and through the product sink. Because we're looking just at the spray dryer, the material properties of interest are mainly thermodynamic. For example, specific heat capacity, absorption isotherm, drying curve and critical moisture, etc. Just to get a feel for what these specifications need to be, let's take a quick look at some of these properties. Here we are looking at the absorption isotherm. We can specify this either as a polynomial or as an Antoine equation, as it is in this example. The mechanistic model is used to simulate the process-product interaction and generates the critical quality values such as powder moisture, particle size distribution, bulk density, etc. From the mechanistic model, we build an optimizer in the advanced process control, and then we can optimize the dryer. This model-based environment allows us to do this readily and quickly and experiment with various optimization scenarios. For example, we can evaluate how the dryer responds to a change in material properties and how the optimization strategy may need to change. We can ask ourselves questions such as, is the operating point affected by the change? Where do I have to shift the dryer operating point to maintain CQ8 in spec while still maximizing capacity and yield? At this point, let's turn to the advanced process control. Here we have a dashboard which shows us on the left hand side a Molly diagram showing the dryer operating point. On the Molly diagram we also have a product sticky curve which is shown as this black curve. Underneath the Molly diagram we have the same representation of the sticky curve, but this time as RH versus temperature, and the exhaust air is shown here. We have a couple of KPIs, the typical things that might be of interest to performance production. So for example, powder moisture and the slurry flow. We have on the right hand side a time-based plot which shows us the inputs into the mechanistic model, and these are set by the APC. So for example, slurry flow and inlet temperature. The mechanistic model then generates process outputs for us, and these in this example are powder moisture, the outlet temperature and the exhaust relative humidity. Sitting behind the dashboard, the advanced process control has an optimizer which is seeking to maximize the slurry flow and the powder moisture while keeping the dryer exhaust inside the sticky curve. Here we can see the optimizer settings. So for example, the inlet flow must be airflow has to be between 1.5 and 2, as these are equipment limits. Currently the airflow is 1.7, and the optimizer is telling us we can reduce this to 1.5. So let's take the optimizer advice, and now let's see this model-based environment in action. First of all, we'll change the gas flow. Currently 1.7, we'll change it to the optimal value of 1.5. For the inlet air temperature, currently 424, the optimizer is telling us the optimal value is 430. So let's change the airflow. And then finally, the slurry flow. Let's change this. The optimizer is telling us we can push all the way to the equipment limit of 0.6. Now we can see on the time-based plot, the dryer is now starting to respond. And on the left-hand side, we can see the dryer exhaust is also starting to move, and we can see that we are starting to get close to the product sticky curve. If we look at the KPIs, following the inside track for moisture, the moisture has now entered into the green range, which is where we want to be in the production environment for pushing moisture. The slurry flow, inside track, has moved all the way to the maximum of 0.6, so we really have pushed this dryer to its maximum capacity. If we look at the Mollier diagram and the RH temperature diagram, we can see the exhaust relative humidity has now been pushed, and we're now at the edge of the product sticky curve, which again is factored into the APC. So the optimizer has pushed us all the way, but no further past the point of product stickiness. We can also see on the time-based plot how the model has generated these changes in powder moisture, outlet temperature and exhaust humidity. In the wider context of formulation design, this model-based approach will start with optimizing the ingredient formulation itself. The model would also include the full set of process steps. So for example, liquid addition, liquid mixing, compounding, heat treatment, evaporation, drying and blending. This concludes the short demonstration I've given you. Remember, we have just focused purely on a spray dryer, just to give you an example of what can be done. But the bigger picture includes the formulation itself all the way through to blending. I hope you found this example informative and it's given you a flavour of just what we can do with this model-based approach. Thank you for your attention and goodbye.